Welcome to iLecture Online, and here's the next topic dealing with capacitors, and in particular, how much energy is stored on a capacitor. And as we saw in previous chapters, when you push charges across the potential difference, you create energy. Actually, you store energy into a device. And so a capacitor is kind of like that. So imagine that you have a capacitor with two parallel capacitor plates, and you connect that to a battery or a voltage source like that. So voltage source equal to V. And let's say the capacitance has capacitor C. And let's put a switch in there so we can kind of go like this. So the switch currently is open, which means there's no charges flowing to the capacitor. And at the moment we close the switch, charges coming from the positive end of the battery will flow through the circuit here and start depositing themselves onto the capacitor plates, and slowly, well, depends, maybe fast, depends what the circuit is made out of, maybe very fast, we'll start putting charges onto the capacitor plate, pushing positive charges away on the other side, making the other side of the plate negative as these positive charges flow back to the negative end of the battery. So by doing that, it has the effect of moving. Every time you put a charge on the side of a capacitor plate, it has the same effect as if you were to take a charge and move it across the gap between the plates. It's like pushing the charge across. So if you remember when we did that before, that the work done to move charges across a gap was equal to the force that they were experienced times the distance that they traveled, and that would be equal to the force in an electric field is equal to E times Q, so that would be E times Q times D, and E times D is the potential difference, so we can write this as E times D times Q, and this here is the same as the potential difference between the plates times Q. So the work done to put each charge on the capacitor plate equals the potential difference at that moment in time times the charge that you just placed there. So you can imagine when you put the first charge there and there's not yet any potential difference between the plates, to put the first charge there, it takes 0 joules. It takes no work at all. But to put the last one there, when you place the last one there, the capacitor is already fully charged, and the potential difference across the plates is essentially the same as the potential difference across the battery, equal to V. So to the work done to put the last one there is equal to the change in potential difference, or V, times the charge on there. So how much energy or how much work do you think it takes to put the middle one there? Let's say you put 1,000 of them on there. The first one would take 0 joules, the last one would take this many joules, and the one in the middle, halfway through, would take half that much. So the work done to put the middle one in there would be on the average of the two, or 1/2 V times Q. So it then follows, by this logic, then if you put all of the charge on there, so that Q is simply the sum of all the little Q's, one at a time. Q is the total charge of all of them put together, that the work done to put the total amount of charge on there would then be equal to 1/2 the voltage times Q. And that would then be the work done to put all of them on there. All right. Now, going back to the definition of capacitance, we can say that the capacitance is simply equal to the ratio of the charge that you put on the capacitor divided by the voltage you put on there. So we could potentially replace Q by C times V, or we could potentially replace V by Q over C. So here I can take this equation and say that Q is equal to C times V, or I can say that V is equal to Q divided by C. So we can take those two equivalents of Q and V, plug them in here, so we can say that the work total can also be expressed as 1/2 times, instead of V, I can write Q over C, so it will be Q over C times Q, which is equal to 1/2 Q squared over C, or I can say that the work total is equal to, and I can take the original equation and replace Q by C times V, so that would be 1/2 V times C times V, or 1/2 V squared C. So these are the three ways in which you can calculate or describe the total work done or the total energy stored on a capacitor when it's filled with charge. And then, of course, if they tell you, for example, that you have a 20-volt battery, and let's say that you have 50 microcoulombs worth of charge on the capacitor, then if you say, well, how much energy is stored in the capacitor, so the energy stored is equal to the work done to put all that charge on there. The work done can be described as 1/2 V times Q. We have the voltage, we have the charge, so we say that's equal to 1/2 V times Q, which is equal to 1/2 times the voltage. The voltage is 20 volts, and the charge Q is 50 times 10 to the minus 6 coulombs, so that would be equal to 1/2 times 20 times 50 is 1,000 times 10 to the minus 6, that would be 1 times 10 to the minus 3, and that would be joules. Voltage times coulombs is joules, and 1/2 that would be equal to 0.5 times 10 to the minus 3 joules. And that would be the total energy on the capacitor, this particular capacitor, if the potential difference is 20 volts and the charge on the capacitor is 50 microcoulombs. And just for, let's see if we remember this, how big is the capacitor? What is the capacitance of a capacitor that will store 50 microcoulombs of charge when there's 20 volts applied? Well, then we go back to that equation right there. We can say that capacitance is equal to the charge divided by the voltage, which is equal to 50 microcoulombs divided by 20 volts, which is equal to 2.5 microfarads. So in this case, we're dealing with a 2.5 microfarad capacitor. And that's how you work with the energy stored in a capacitor when you fill it full of charge. All right, hopefully that helps. A little side topic, but you never know. You probably will run into some homework problems just like it on your homework. All right, good luck with these.